At this point, you gotta know somebody's gonna say something to you if you're not learning this,
Oh,
right? You gotta kind of expect that. Okay. All right. I am now in teaching mode. Okay, so last time, where did we leave off? Anybody remember? You don't remember, I'm probably doing a pretty bad job teaching.
it was linear combinations and how you can turn them into augmented matrices with it.
Right, exactly. So we had some vectors, let's say, vectors, and we picked some dimension for the vectors. So Rn. Then we could specify a linear combination of these, and we did it using, for the weights, we used x1 up through xk. That's how many vectors we have. Doesn't really look like a k. Just my bad handwriting. Okay. So x1 v1 plus x2 v2 plus dot 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 plus xk vk equals b. So this is a linear combination of the vectors v1 up to vk, and b is the vector that we get as a result. So today we are going to introduce a convenient way to write this, and we refer to this because we're using vectors as objects in this equation. We call this the vector equation. For obvious reasons. The reason I just said. But it's pretty clear what I mean by that. What we mean by that. Vectors, vector equation. It involves vectors. Okay, today we're going to introduce the matrix equation, writing this same equation right here in the form of matrices and vectors and the equal symbol. Okay, so a convenient way to write this is v1, v2, vk. I'm going to go ahead and give this vector name. I'm going to call it capital A. So this is a matrix. Oh, we can even say what the size is. How many rows does this thing have? Yeah, maybe I should have gone a little further before I asked that question. The columns of this matrix are these vectors. The vectors v1 is equal to, well, I'll call it entries, alpha 1, alpha 2, alpha n. Because these come from Rn, each of these columns has a height of n, right? Remember when we talked about representing a vector as a column matrix? So this is an n×1 matrix. It's a column matrix, and this is sort of the conventional way to represent vectors in the way that we're going to talk about this. Okay, so this is a matrix where the columns are v1, v2 up to vk. So now, how many rows? I didn't mean to set you up with that question, I promise. So how many rows? And how many columns? Okay. Yeah, exactly. Perfect. This is an n by k. With columns vectors v1 up to vk in that order. So this gives us some matrix, and we are going to also have a column vector that represents a column matrix that represents the vector x1, x2 up to xk. So x1, x2, xk. And I'm just going to call this vector x. It's going to look like a variable. Well, the variable is going to be, it's going to be a vector variable. So x is a k by 1 matrix. And, well, I was going to write representing the vector x1, x2, up to xk. Really, this is how we write vectors now. So this is the language that we're going to use. So this vector equation can now be rewritten as ax equals b. So this is, at this point, this is just going to be a definition. We're just defining ax. So we define ax equals b to be to represent instead of writing this again, I'm just going to call this equation 1. So that's equation 1. So far I've just given it, yes.
So A is a matrix of vectors, and then X is just a column vector, right?
Yeah, exactly. So, I probably should have spent a little time preparing the way for this example, or for this definition. This is not the notation that we've used so far to represent matrices, right? This is a common and valid notation for writing matrices. So if we want to represent a matrix, if we have a bunch of columns, and we want to just say the matrix with those columns, this is the way we write it. V1, V2, V2. That's what I should have said that before. All right. So this is a definition. This is a sort of a shorthand to represent this, but looking at it from this point of view, what we're doing is we're, in essence, defining the multiplication of a matrix and a vector, which if you'll remember, is a column matrix. A matrix with just one column. So we're doing something like defining a definition, defining a multiplication of a matrix and a matrix. So far, this is as far as we've gotten. Now, in order for this equation to make sense, we need to have as many entries in x, so x1, x2 up to xk, that has to match the number of vectors over here. Otherwise, this equation is not defined. So this is only defined, it only makes sense if the number of columns in A equals the number of rows or entries, because the rows are just just an individual scalar, equals the number of rows in X. And there's a clever, nice way to remember this. This was an n by k matrix. Okay? So that's an n by k matrix A. There is X, which is a k by 1 matrix. And then what do we get out? This is equal to B. Now you're going to have to tell me, what are the dimensions of B? What is the shape of B?
N by 1.
Should be n by 1. Right, we're taking a linear combination of n-dimensional vectors. So what we should get out of the n is an n-dimensional vector, right?
I don't know, I was just looking at the thing up to the right of that, where it says n by 1. B1 equals
Well,
alpha.
that's right, yeah. So these vectors, that's what I said.
I'm not that smart, I just looked at the thing on the board.
Oh, you just took a guess.
No, I just looked at, because you were explaining there, I didn't figure out from that equation, I just figured out because you wrote it.
Okay.
Well, I said n by 1.
Well,
Never mind, sorry.
let's take that answer, which is correct, and make it a little deeper.
Yeah.
Okay, which is, when we're doing this, each of these multiplications we're taking an n by 1 matrix, an n-dimensional vector, and we're multiplying it by a scalar. We get back an n-dimensional vector, right? So each of these things is going to be an n by 1 matrix. Right? It's going to be an n-dimensional vector. I'm saying those things, I'm switching back and forth to really drive it home that these things are the same. Now I do addition of all these things, addition. And we know how addition works, it's just component-wise. I add two n-dimensional vectors together, another n-dimensional vector. And that's what I've got here at the output, B. Does that make sense?
So, what does it exactly represent? Like, I see the map and I'm just putting together, but like, what does that even say about the matrix, these vectors?
Well, what it says about these vectors, the relationship between the set of vectors, let's write that down. B is in, remember I used this symbol before, I'm going to continue to use this symbol. B is in the span of V1 up to Vk. Right? If we pick some values of x1 up to xk, we get a B out at the end. We do these multiplications, we add everything together, and what we get out at the end is a vector. Right? So if B can be written as a linear combination, so this is a linear combination of these vectors, then it must be in the span, because the span is all of the linear combinations.
Okay, so like, it's not always gonna be like just a scalar value.
Is what it is.
B.
No, that's what we were just talking about. So B must be, the reasoning that we just went through, an n by 1 matrix. This multiplication only makes sense, it's only defined, if we have a matching number of vectors and weights. So this is a matrix where the columns are these vectors V1 up to Vk. There's k of them, and each of them has n entries. So this is an n by k matrix, right? Setting the columns like this. And we multiply it by x. This is the vector that contains the weights. There's k of them because there's k vectors. And so the linear combination is defined. The linear combination that we're trying to represent by this multiplication is defined. So it must have the multiplication, the dimensions of the two matrices must have this form in order for it to make sense. Otherwise it doesn't mean anything. We can't say that it means something like this, right? And the output, the actual linear combination that we get as a result, has to be an n by 1 matrix, otherwise it doesn't make sense. So what we're trying to actually represent is this linear combination, this action of combining them, combining the vectors together. Think of this as like taking a bunch of vectors and kind of mixing them, right? Each of the vectors is an ingredient. The weight tells me how much of that ingredient I'm throwing into the pot. This is the soup. So, I wanted to extend that analogy just for a second. Let's say this is chicken, this is onions, and this is cabbage. B is not, if B is beef stew, it's not in the linear combination of these things, right?
So could you use this to like transition between like two different coordinate systems? That maybe one's just like defined out like the slight out this has a grid on it this way and then shifts everything?
Wait a few weeks
Okay.
till we get to that subject.
Alright.
We'll have to define what a coordinate system means. Yeah, but you're on the right track. Now, what was your question?
I was gonna say,
Actually, first, what is your name?
Andrew,
Andrew. I'm gonna ask people, I really wanna like refer to people by their names, even though it's hard to tell who you are with your mask on. And I'm gonna forget, I promise, but Andrew, what was your question?
so saying that that equation has a solution is the same as saying that B is in the span, like those are the same statement.
Again, I was just about to say this, but you're right, yeah, that's perfect. If B is not in the span of this, then we cannot find x1, x2 up to xk. So we can go in two directions. First direction, we can pick an x1 up to xk, we can pick the vector x, and then we can shove it into this equation and get a vector out. That's one direction. The other direction is we can start from a B, and we can work our way backwards and say, what are the x1 up, x2 up to xk that give me that B? And I think last time we even talked about how to do that. So let's say B is in the span of this. So let me fill in what you were saying. The equation, that's even worse. The equation AX equals B, it has a solution. I'm not sparing you the mathematical notation. We say the phrase if and only if. I'm gonna finish. If and only if this. B is in the span of B1 up to BK. So what do I mean by, first of all, what do I mean by if and only if? If you haven't heard this before, you probably have heard this before, the math concept. But it's a very specific logical meaning. What we mean is, if the equation has a solution, then B is in that span. And if B is in the span, then this equation has a solution. They're identical in terms of their truth. If this is true, then this is true. And if this is false, then this is false. They're true and false at the same time. And we shorten if and only if by writing if with two F's instead of one. It's like if, but it's much stronger. It really is much stronger. Any more questions about this? Let's take it one step further. If and only if is kind of a way of saying these two things are logically equivalent. Really, they mean the same thing. AX equals B has a solution is exactly the same kind of statement as B belongs to the span of this. In the same way that the statement x plus y equals 1 is equivalent to 2x plus 2y equals 2. Really saying these contain the same information. So another way to say this is true if and only if this is true, if and only if the system of linear equations. I have to write it so many times, I'm just gonna abbreviate it. The system of linear equations represented by the augmented matrix. Remember back to day 2 of class. The augmented matrix we can take a system of linear equations and turn it into an augmented matrix. And go in the opposite direction, we can take an augmented matrix and turn it into a linear system. System of linear equations. Now I'm going to write that matrix. And I'm continuing with this notation, this kind of notation that I didn't do a good job. Well, I'm really going to hammer it home now. If these are column vectors, then we can form this matrix just by stacking the column vectors next to each other. Same thing happens here. This matrix, the matrix that I'm specifying here, is the matrix A, and then I just put another column on the end, which is B. So this is the augmented matrix that's the same as B1, B2, BK, B. Which is the same as, what did I say the B's were? Alpha. So B1 is alpha 1, alpha 2, and alpha n. And V2, I'm representing as beta 1, beta 2, going to beta n. And then I've got some more columns, V3, V4, V5, all the way up to VK. VK is, what's next? Gamma, gamma 1, gamma 2, and gamma n. So that's all the columns, that's all the entries of A. So each of these columns. And then B, which I'm going to write B1, B2, down to Bn, very badly. And I need to finish the sentence. The system of linear equations represented by this augmented matrix has a solution. And these are all the same solution. Right. The solution x here is the same x that you would get if you tried to figure out what combination of these vectors, although specific, if we're being really specific, when I specify that this is a span over this set of vectors, the set doesn't intrinsically have an ordering. And so I might have to swap the weights around. I might have to permute them to get them in the same order that they would be in this right here, or they would be if I turn this augmented matrix into a system of linear equations. Does that make sense? I'm asking you specifically.
Oh, me?
Yes, based on the look on your face.
I,
On the small part of your face I can see.
you wanna know the last line I wrote in my notebook?
Sure.
He's writing a bunch of stuff on the board, but I'm really not following it, and that's to remind me tonight, tomorrow, to go back and watch this lecture with the book and just try and figure it all out.
Tonight is tonight, tomorrow's tomorrow, but why not right now? Let's go.
I'm trying.
Okay. No, I mean, I should be trying.
I do have a relevant question. So this does not seem to be exactly, I was thinking I should read the book, do the homework, and then the next day we kind of discuss that material in class. But should I be trying to do the next section of the book, the next section of the homework before we discuss the material?
So on the schedule, we are scheduled to discuss section 1.4.
Oh,
Which is this.
4 today.
Yeah.
Okay.
That's what's on the schedule.
All right, so I need to get a couple sections ahead of what's due.
Well, okay, so this is the ideal way that this will go. You look at the schedule,
Okay.
it says Wednesday, today's Wednesday. Wednesday, February the blah, blah, blah. We will be talking about section 1.4. So read section 1.4 before you come in.
Okay, and that's
You know
on
what
the
I'm saying?
syllabus.
That's on the first page of Canvas, the first thing that pops up when you go to it.
I'm sorry, I'm still getting oriented to all my classes. So.
Fine.
All right, well, that really helps.
It's totally fine, that's, I want to find out about these things. But, what was the point of all that? Let me make a little divider here between this, because it looks like this is running into that. Okay. And this, all right. So what we basically said is that if we take a set of vectors, we have this linear combination that lets us kind of mix them together and produce something else. We want to figure out if we have a set of weights, if we have an x1 up to xk, what's the vector that we get out? Well, that's just multiplying these by the vectors and adding them together. Next, we want to figure out if we can go in the other direction. If we're given a b, can we figure out this x with the vector? And I should slow down. I feel like I'm talking really fast too. The x that represents the weights, how we mix them together. Can we figure out if there's an x that gives us a speed? And if so, what is it? Now we're saying, because of what this means, this equation has a solution if and only if the speed is in the span, if and only if the system of linear equations, this right here, has a solution. And in fact, this system of linear equations will give us this solution. It will give us x. And on top of that, we know how to solve an augmented matrix. We know how to row reduce an augmented matrix, which is the same thing as solving this. So maybe this is a good time to do an example. Can I borrow the one from the book? Because again, this involves a lot of writing. I'm thinking maybe I'll make like a PowerPoint of these examples, and then I can just hit a button instead of writing, but you have to write. Maybe that's not fair. Okay. I've just given up, by the way. I'm saying okay after everything. It's just who I am. I just have to accept it. 3, 2, minus 2. 4 minus 6, minus 7. And B, we should do a specific example before that I do the general one that's in the book. No, I went straight into it. So we're going to say this is a general B. What is a general B? It's a B where all of the entries are undetermined. We're just going to put variables in there, and we're going to try to figure out when we can solve this thing. So B1, B2, B3. So we're trying to, we want x so that ax equals b. Right? So based on what we've said here, we can take this thing, this A and this B, we can turn them into the augmented matrix AB, and then we can do the row reduction. So let's do it. So AB is this augmented matrix. Now let's go to work row reducing. Work from the book so that I don't. I'm going to do a replacement and another replacement to get rid of this row and get rid of this row, or get rid of the entries in this row. What do I get? I get the matrix. I should have it over here. 1, 0, 0, 3, 14, 7, 4, 10, 5. Make it divided here. So we multiplied this by 4 and added it to this to get rid of this negative 4, and that gave us 14 and 10 here. But on the b's, what we get is, well, this one stays b1. This one is b2 plus 4b1. Right? We added 4 times this to this. And then 3 times this to this. So we get b3 plus 3b1.
Is that 4, 10, 5?
4, 10, 5?
Okay.
Yes. My handwriting?
I just, something, yeah, well, it was more like I thought I heard a 3, but it looked more like a 5, and that was my bad.
Okay. I may have said 3.
No, you probably said 5.
Okay.
I'm a couple lines behind if you.
All right, I'll slow down a little bit. So now I'm going to do another replacement. I'm going to use this entry. No. What am I saying? This is my first pivot. And then I ignore this, that's the row reduction algorithm. This is my next pivot. So I'm going to multiply this row by negative 1/2 and add it to this row. What do I get as a result? 1, 0, 0, 3. It better be 0 here. No, I'm sorry. It better be 0 here. And then if I multiply this by negative 1/2 and add it to this, I get 0 again. This remains b1. This is b2 plus 4b1. This is the row that we're eliminating things from. We get b3 plus 3b1. And then minus 1/2 times this right here, which is b2 plus 4b1. Which we could simplify if we'd like. But what does this mean? What's the constraint that this tells us about b? Can b just be anything?
All those have to equal 0.
This row right here